Hi, I'm Quinn. Today I'll be doing the AP Calculus BC FRQ, specifically number 6. I will be covering slope fields, logistic growth, Euler's method, Taylor polynomials, and range because I love calculus. We're given a differential equation and an initial condition, and we're asked to draw the solution curves through 3, 2 and 0, 8. With this slope field, we have tangent line approximations at different points, so we can see that the slope will increase, then start to level out. So I'll just follow the pattern of the tangent lines and draw the curve from 3, 2. It starts to level out near the asymptote, and then also the other way. And then from 0, 8, I'll follow the pattern again, and it's also leveling out near the asymptote. Oh, be careful not to cross over the asymptote, and keep your solution curve slightly above it. Another way to approach this problem is recognizing it's a logistic growth function following the pattern of dp dt equals kp times 1 minus p over m. We have dy dt is equal to 3/4 y times 1 minus y over 6. So I just divided by 6 on the inside, multiplied by 6 on the outside. So our m value right here will be equal to 6, and this is the carrying capacity, which is why we see this asymptote at 6, and then m over 2 is the point of inflection, so 6 divided by 2 equals 3 is where we'll see this maximum slope, and then it will level out on either side. The College Board would award 1 point for the solution curve through 0, 8, and another point for the solution curve through 3, 2. In slope fields, you follow the pattern of tangent lines. You can compare this to following the pattern of colored rocks in rock climbing. Part B asks us to use Euler's, not Euler's method, to approximate f of 1. We're starting at t equals 0, and then we need 2 equal steps to get to 1. That means we'll use our intermediate step of 0.5 because 0 plus 0.5 plus 0.5 equals 1. I set up this table with ty and dy dt so I can easily make tangent line approximations at each t value. So 0, 8 is our initial condition. I'll find dy dt by plugging t equals 0 and y equals 8 into this differential equation, and I get dy dt equals -2. So my equation here will be y equals -2 t minus 0 plus 8. To get my new y value at t equals 0.5, I'll plug in 0.5 for t, so I get -2 times 0.5 plus 8, and this will give me 7 for y. And now I plug in 7 into the dy dt equation, and I get -7/8. This will be the slope for our new equation, -7/8 t minus 0.5, the t value, plus 7. Notice that when I plug in 1 to this equation, I get -7/8 times 0.5. Again, we get 0.5. The 0.5 term should be the same each time whenever we have equal steps, so you can use that to check your work. And then plus 7. This expression gives me y for f of 1 is approximately 105/16. Make sure this is an approximation size. The College Board would award 1 point for the correct 2-step Euler's method and 1 point for the correct approximation of f of 1. In Part C, we're asked to find the second-degree Taylor polynomial about t equals 0. So this could be referred to as a Maclaurin series, and we're just finding the polynomial to approximate f of 1. Sometimes we're given something easier, like some manipulation of 1/1 minus x, and we can use our known n equals 0 to infinity x to the n Taylor series to help build our polynomial. But since we are not, we have to build it from scratch. So from the initial condition, we have f of 0 equals 8. We can easily find f prime of 0 by plugging in 8, our y value, into this dy dt expression, and we get -2. Be careful not to plug in 0 into this expression because the y value is 8. Now, to find f double prime of 0, we first need to find the second derivative. So I'll start by distributing the dy dt equation, and we get 3/4 y minus 1/8 y squared. To take the derivative, we have to remember chain rule. So our second derivative will equal 3/4 times dy dt. Remember, this isn't just times 1, this is dy dt. And we subtract 2 times 1/8 is 1/4 times y, and again we have to multiply by dy dt. Now we can plug in 0 into this equation, so we get 3/4 times our dy dt, -2, and we subtract 1/4 times our 8, which is our y value, times -2, our dy dt, and we get 5/2. Now it's time to build our Taylor polynomial. We can use this known Taylor series function to help us. So f to the n of a divided by n factorial times x minus a to the n, where a goes to 0 because it's centered about t equals 0. So this will be 8 times x to the 0 over 0 factorial minus 2 times x to the 1 over 1 factorial plus 5/2 x squared over 2 factorial. We can clean this up a bit, and we get 8 minus 2x plus 5/4 x squared. Now, you'll see I made a mistake. I used x's instead of t's. Since the original problem had t's, we need to leave this as t. So our polynomial is 8 minus 2t plus 5/4 t squared. Now, we can use this polynomial to help approximate f of 1. We're simply going to plug in 1 to this equation, so we have 8 minus 2 plus 5/4. Therefore, f of 1 is approximately, not equal to, 29/4. The College Board would award 2 points for the correct second derivative, 1 point for the correct Taylor polynomial of second degree, and 1 point for the correct approximation of f of 1. In part D, we're asked to find the range of f where t is greater than or equal to 0. From part A, we know the graph looks something like this, with an asymptote at 6 and a point at 8. And we are given the initial condition f of 0 equals 8, and the domain is t is greater than or equal to 0. So although the slope field showed the graph going up past 8, that is outside the domain. So our greatest value will be 8 in a closed bracket because 0, 8 is an actual point, and t can be equal to 0. The lowest value will be 6 because the graph will not pass below this asymptote, and we have to keep it in an open parenthesis because the asymptote does not allow the graph to actually reach 6. This problem was generally pretty easy, but be careful not to overcomplicate it and think it's harder than it is. The College Board awarded 1 point for the correct answer with the correct parentheses, 6, 8. For more practice, see 2000 BC FRQ number 6, 2007 BC FRQ number 5, specifically Form B, and 2017 BC FRQ number 6.